The search for life beyond our planet has captivated the human imagination for centuries. From science fiction to scientific exploration, the possibility of extraterrestrial life has driven scientists to explore our own solar system and beyond. One of the most promising places to look for life within our solar system is Jupiter's moon, Europa. Europa is one of the 4 Galilean moons of Jupiter, discovered by Galileo Galilei in 1610. It is the smallest of the 4 moons, but its surface is unique among them. It is covered in a thick layer of ice, with deep cracks and fissures visible on its surface. It is believed that beneath this icy shell lies a vast ocean, kept warm by the tidal forces of Jupiter's gravity. The radiation coming from Jupiter on the ice results in the release of trapped oxygen, which is the most abundant element of Europa's atmosphere. On Earth, oxygen is the most vital element for the organic chemistry process. If the oxygen can get under the ice of Europa, then it can be the key ingredient for life to exist on Europa, even if it's microorganisms such as bacteria. Another possibility of life on Europa is to have anaerobic organisms that don't require oxygen to survive. These creatures used to dominate the Earth in its early days. At last, the possibility of life near the volcanic activity under the Europa Ocean is also considered. In the depth of Earth's at the boundary of continental plates, the hydrothermal flow releases the essential minerals such that life can develop here. The first life on Earth is said to have developed in a similar way. The idea that Europa might harbor life is not new. In fact, it has been a topic of scientific speculation for decades. The conditions beneath the icy shell of Europa, with its liquid water, warmth, and minerals, are similar to those that exist on Earth, where life is known to thrive. But until recently, we had no way of exploring this hidden ocean. In 1979, the Voyager 2 spacecraft made a flyby of Europa, providing the first close-up images of the Moon's surface. In the decades that followed, several other spacecraft visited the Jovian system, including the Galileo mission, which orbited Jupiter for 8 years from 1995 to 2003. These missions provided valuable insights into Europa's geology and surface features, but it wasn't until the 2010s that the possibility of exploring Europa's ocean became a reality. In 2011, NASA launched the Juno spacecraft, which is currently orbiting Jupiter. One of Juno's objectives is to study the gravitational field of Jupiter, which will help scientists understand the interior structure of the gas giant and its moons. But the real excitement for Europa exploration began in 2012 when NASA announced the Europa Clipper mission. The Europa Clipper is a spacecraft designed to study Europa from orbit. It is set to launch in the mid-2020s and will conduct multiple flybys of the Moon, using a suite of scientific instruments to study its surface, ice shell, and subsurface ocean. The mission's objectives are to study the potential habitability of Europa, search for signs of life, and gather data that could help in the planning of future missions to Europa. But perhaps the most ambitious mission to Europa is the Europa Lander, a proposed mission that would land a spacecraft on the surface of Europa and drill through the icy shell to explore the ocean below. This mission is still in the planning stages, with no set launch date, but it represents the next step in our exploration of this fascinating moon. But one concept that has been gaining attention in recent years is the idea of sending a Cryobot and Hydrobot to Europa. The Europa Cryobot is a robotic probe designed to penetrate the thick ice crust of Europa and explore the ocean below. The probe would be equipped with a range of scientific instruments, including multiple sensors and sampling tools, which would allow it to study the composition, chemistry, and potential habitability of the subsurface ocean. The idea behind the Europa exploration is relatively simple. The probe would be launched from Earth and sent on a trajectory to Europa. Once it arrived at the Moon, it would use a propulsion system to slow itself down and land on the surface. Then, it would deploy a drilling apparatus, which would bore its way down through the ice. As the probe descended deeper into the crust, it would take measurements and collect data about the environment, transmitting this information back to Earth. One of the key advantages of the Europa Cryobot is its ability to explore areas of the subsurface ocean that are inaccessible to other types of spacecraft or rovers. The Cryobot could access parts of the ocean that are shielded from radiation and other harsh conditions that can make it difficult for life to survive. Another advantage of the Europa Cryobot is its potential for long-duration exploration. The probe would be designed to operate for an extended period of time, potentially years, allowing it to collect a large amount of data and monitor changes in the ocean over time. One of the recent developments in Cryobot is the Valkyrie developed by the Stone Aerospace. The initial prototype descends at a depth of 30.52 meters at an average rate of 0.9 meters per hour using active jetting. It consists of multiple subsystems that include beam dump and pressure housing, heat exchangers, hot water jets, filters and pumps, beam dispersion optics, onboard control computer, high-power laser fiber field junction laser power, and communications and liquid cooling umbilical. The Valkyrie uses a multi-mode continuous wave 1070 nm diode pumped ytterbium fiber laser with a nominal output of 5 watts and a power conversion efficiency is 35%. Future lasers of 100 kilowatts will be able to penetrate 3 kilometers of ice in days instead of months. However, there are also significant challenges associated with the Europa Cryobot concept. One of the biggest challenges is the harsh environment that the probe would have to operate in. Europa's subsurface ocean is under immense pressure and temperatures are extremely low, requiring the Cryobot to be designed to withstand these conditions. Additionally, the Europa Cryobot would need to be highly autonomous, as communication with Earth would be limited due to the thick ice layer. This would require sophisticated onboard computing and control systems, as well as advanced imaging and sensing capabilities. Despite these challenges, the Europa Cryobot represents an exciting and innovative concept for exploring Europa's subsurface ocean. It has the potential to revolutionize our understanding of the universe and the potential for life beyond our own planet. Once the Cryobot reaches the ocean, a Hydrobot will be released. A Hydrobot, as the name suggests, is a robot designed for underwater exploration. The idea of using a Hydrobot to explore the ocean beneath Europa's icy shell is not new, but recent technological advancements have made it more feasible. Once in the ocean, the Hydrobot would explore and collect data about the environment, potentially even searching for signs of life. The Europa Hydrobot concept is still in the early stages of development, but there are several reasons why it has gained traction among scientists and space exploration enthusiasts. For one, a Hydrobot would be able to explore areas that are difficult or impossible to reach with a spacecraft or rover. It would also be able to take samples and measurements directly from the ocean, providing a more comprehensive understanding of the environment. Another advantage of the Hydrobot concept is that it would be able to operate for an extended period of time. Unlike a spacecraft or rover, which has a limited power supply and must be carefully managed, a Hydrobot could potentially operate for years or even decades in Europa's subsurface ocean. This would allow for a more thorough exploration of the environment and potentially increase the chances of finding signs of life. One of the proposed ideas for Europa Hydrobot is a miniature autonomous submersible explorer. The Hydrobot's shape can be based on the fusiform shape, similar to that of dolphins with a rounded leading edge and slow tapering tail. Such a shape can provide a small drag coefficient of 0.024 and an easy interchange of instrument modules. The maximum range of Hydrobot is dependent on several factors such as mass, motor efficiency, propeller efficiency, and fluid density. And range can be calculated with the following formula. For buoyancy control, a near-neutral buoyancy will be required for slow-speed maneuvers or hovering capability. The optimal method to control buoyancy is to partially fill the fiber spool chamber with buoyant glass microspheres and release these in a controlled manner. The Hydrobot will have several subsystems such as a navigation camera, communication and data handling, an onboard computer with acoustic distance sensor, a motor, and a power source. In order to sustain a long lifetime, the probe requires a significant amount of energy. As Europa gets 25 times less sunlight than the Earth, solar energy as a power source is not feasible for the probe. The optimum method for a power source would be a miniature reactor. The nuclear fission reactor uses a uranium-molybdenum alloy as a fuel source. The sodium heat pipes are connected to the reactor core to carry the heated vapor up to the Stirling power conversion system. The power conversion requires a temperature difference to keep the reactor from overheating. The reactor is able to produce over 4 kilowatts of power at 800 degrees Celsius, and a similar reactor was used in Cassini supplying 870 watts of power. A high communication rate can be obtained once the Hydrobot scans the area and transfers the data through a Cryobot by a docking mechanism. The Cryobot connects with the lander with a fiber optic tether which at the end transfers the valuable data back to the Earth. This will require the Hydrobot to be highly reliable and autonomous. As the Hydrobot scans the Europa Ocean, it will search for signs of life such as hydrothermal vents using side sonar flash photography, and chemical and thermal sensors that will allow Hydrobot to accurately locate the vent and take samples from the vent. The Hydrobot consists of an image compressor that will consume about 2,000 images, each of 4 megapixels with 24-bit color resolution, and the camera creates typically file sizes of roughly 260 kilobyte. A minimum storage of 2 megabits will be required for the mission. However, the Hydrobot can store 0.25 gigabits of data, which is equal to about 120 compressed images. An estimated 2 frames per second can be transferred, resulting in a transfer speed of 1 megabyte per second. The pressure and temperature in Europa's subsurface ocean are extreme, and the Hydrobot would have to be designed to withstand these conditions. It would also have to be able to navigate through the ocean and communicate with Earth, which would be a significant technical challenge. The possibility of finding life on Europa, or any other world beyond our own, would have profound implications for our understanding of the nature of life itself. It would also raise questions about our responsibilities as stewards of the universe and our relationship with other forms of life. The Europa Cryobot and Hydrobot concept is still in the early stages of development, and there is much work to be done before it becomes a reality. However, the potential rewards of this mission are enormous, and the idea of exploring the ocean beneath Europa's icy shell is both exciting and inspiring. Exploring Europa is not without its challenges. The harsh radiation environment around Jupiter presents a significant risk to spacecraft and their instruments. The cost of launching and operating a mission to Europa is also high, and there is always the risk of technical failure or budget cuts. But the potential rewards of exploring Europa, and other worlds like it, make it a worthwhile endeavor. The exploration of Europa represents the culmination of centuries of scientific inquiry and the human quest for knowledge. It is a testament to our curiosity, imagination, and ingenuity. This video is based on the chapter case study, Robotic Exploration of Europa in the book Planetary Rovers by Ellery and submitted to the Robotics Department of the University of Würzburg for the Planetary Exploration Seminar.